Hi class, this is lecture 16 for Econ 4001.02, and I'm your professor, John Raybeck. Thanks for listening. So this lecture is going to cover solving the problem with quasi-linear utility. And this will be the most difficult case, but also kind of the most interesting one because it shows how, sometimes these things don't work out with nice analytical forms, and that's actually okay. So recall that quasi-linear utility maximization is when we have some function v x1 where an individual wants to maximize the utility given by v x1 plus x2 subject to the budget constraint here. So we'll normally make the assumption that v is increasing. But regardless of this, I can always add more x2 to my budget and increase my utility. So we'll know, again, the budget constraint will bind in general, but now it's going to get more complicated when it binds. So this will require us to use more complicated Lagrangian methods, but the thing I want you to take away from this is basically there's going to be cases. Right, so, and I'll explain why on the next slide. So suppose we just want to look at a quasi-linear utility maximization graph. Again, we'll put good 2 on the vertical axis and good 1 on the horizontal axis. So here's good 1. And here's good 2. Right, and again, we'll put our budget constraint here in orange. And here we have M over P2 and M over P1. The biggest issue is with this, we're going to have utility functions. Unlike, so Cobb-Douglas here, I'll use in red, never intersects the axis, right? So this means that we're never going to be able to have these boundary conditions take place, and you're never going to purchase just one good and none of the others. So in this case, we can have things that look like this. But this means that there will be cases where, maybe you're best off, here is an example of utility functions where you're best off at this, but there could be other ones where you're not going to be better off at the budget, right? So if I put in this alternative budget in brown, like this, I'm going to be at the extreme point. And similarly, if I have a budget in pink that's like this, I could be at this other extreme point. So now those budget conditions that we didn't need to pay attention to in the other case, we actually need to pay attention to them here. So we're going to set up a Lagrangian and solve this, the method, right? So there's no way to keep track of everything with all of the things going on. But this Lagrangian is going to be a bit more complicated. One nice thing to note is that if you have the limit of the marginal utility of the utility function going to infinity, then you only have one boundary condition to worry about, right? Because if this is the case, then we know x1 star is strictly greater than 0. And then this will tell us that mu1 is equal to 0 in our Lagrangian, where I'll show you what this mu1 is going to be in just a little bit. So in the other case, we'll need to use 2 additional Lagrange multipliers. And that'll show up in the Lagrangian that we write down in the next slide. And when we solve this. Right, so clear the drawings. So here we're trying to do the Lagrangian. And the Lagrangian with respect to, now it's going to be x, lambda, mu1, and mu2. Right, so let's write down the Lagrangian. We have v of x1 plus x2 plus lambda times the budget constraint so we put this here. So we have m minus p1 minus p2. And then we're going to have these new terms. So this will be plus mu1 x1 plus mu2 of x2. So this is the problem we want to solve now. And the thing that's going to go on here is we're going to check 3 cases. So mu1 equals 0, mu2 equals 0, mu1 greater than 0, mu2 equals 0, and mu1 less than 0. Or sorry, whoops. And also mu1 equals 0, mu2 strictly greater than 0. So recall this thing we said before. So if mu1, we need these mu1 x1 equals 0. And similarly, we need mu2 x2 to also equal 0. Right, so if mu2 is greater than 0, this means that, so the key thing is mu n strictly greater than 0 is going to imply that x of n is equal to 0. So what I'll do is write down the first order conditions, and then we'll need to break up our solution into cases, basically. And we're going to assume some additional things along the way, but these won't be, anything too horrible, hopefully. So looking at the first order condition, if I first take the derivative with respect to x1, then this is going to be v prime x1, right? So this is a function that only depends on x1, so I'm not going to write the normal long partial derivative definition here. This will be plus lambda x1, or sorry, minus lambda p1 and we're also going to do plus mu1, right? So this mu1 is the new thing here. We'll also look at the partial derivative of our Lagrangian with respect to x2. And in this case, it'll be actually a little nice because we'll just have a 1 here, right? So we have this linear part of x2, where this is just a 1 in front of it, we'll have a minus lambda p2, and then a plus mu2 equals 0. And we'll use the budget constraint when we need to, but it'll always just kind of be floating in the background, right? So budget constraint, let me see, I'll put it down here, is going to be P1 x1 plus P2 x2 is equal to m. Yeah, so this is the budget constraint, and these are the conditions we're going to be dealing with. So the first one is, let's assume mu1 equals mu2 equals 0. And here, if we do this, these will both be gone, right? And I'm going to keep this first order condition up just because it'll be useful to refer to rather than writing things down all the time. But we can then simplify this condition to just get that lambda is equal to 1 over P2. But if we have this, we can plug it into this equation, and this will tell us that, v prime of x is equal to P1 over P2, right? So what this tells us is that, the amount of good 1 that I purchased only depends on P1 and P2. And we can write x1 star then as equal to v prime inverse of P1 over P2. Finally, we're able to get x2 star by plugging this into the budget constraint, right? So here we get x2 star then is equal to m over P2 minus P1 over P2 v prime inverse P1 over P2. So this is a solution. But here we have mu1 and mu2 equal to 0. So, what we really need here for this is that this here needs to be strictly greater than 0, right? So this is going to define a case for us, right? So we need this to hold if we're in this case. So we'll keep that around here. And we'll just kind of throw this information, partly over to the side here so it doesn't get in our way. But we'll use it again later. So there we go. And then now I'm going to get rid of my work to solve this first case. Right, so there we go. That was case 1. I'm going to do case 2 in a different color, so we'll do case 2 in green. So this is going to be mu1 greater than 0, and mu2 equals 0. So this tells us that x1 star is equal to 0, and x2 star then by plugging this into the budget constraint, we get that x2 star is just equal to m over p2. However, the issue is we don't really know when this occurs yet, right? So the way we get this is we start to plug this information into this, the first order conditions, right? So if we do this, here again, we have mu2 is equal to 0. So this implies that lambda is equal to 1 over p2. And similarly, we'll also get an expression for mu1, right? So we can plug this into here, and then we get mu1 is equal to, p1 over p2 minus v prime of 0. Right, but here we assume that this was greater than 0, so this also needs to be greater than 0 for a case. Right, so this is going to be the thing that defines this case, similar to how this condition for x2 star defined the previous case. So I'll just shrink this down a little bit and save it for later. So I'll put that over there. And then also we have this as well, right? So when this is the case, we can put this here. Also, if you look at the case here, you can see why if v prime of 0 goes to infinity, we can never have this condition hold, right? So mu1 needs to be positive, but in fact, v prime of 0 would equal infinity, so we get negative infinity here. So it would never, work in order to get this case. The final case we'll do in a different color. So I guess I'll do purple here. So now we have mu1 equals 0 and mu2 greater than 0, right? So here mu1 equal to 0 is going to imply that, or sorry, mu2 greater than 0 is going to imply that x2 star is equal to 0. And, again, plugging this into the budget constraint, we get that x1 star is equal to m over p1. Right, so we're going to just spend all of our income on good 1. Now, again, we need to find the condition where mu2 is strictly greater than 0. Now we're not able to find an expression of lambda from this equation. So instead, we plug our information into this equation. And if we do this, we know that mu1 is equal to 0. So in fact, we'll, if we expand this out, we get lambda is equal to v prime m over p1 divided by p1. Right, so now we're evaluating the derivative of v at m over p1 and dividing that by p1. From there, we plug this into this equation here, but then we get mu2 is equal to v prime m over p1 over p1, times p2 over p1, and then minus 1. And the thing that we need here is that this is greater than 0. Right, so this is the condition, and those are the solutions. So now that we have this, this gives us the condition, for this one, for this case. So, put this over here. Just simplify that. And we have these things here. Great. So that's all of the information now for the solutions. So how do we write all of this down then? So I'm just going to get rid of this because it's going to take up some space. The way we're going to do this is, we'll have x1 star is a function of p and m. And this is going to equal some stuff that depends on cases, right? So we'll have solutions, m over p2 minus p1 over p2 v prime inverse p1 over p2 oh, sorry, that's x2. So let me just move this out of the way. So if this here, if this is the case, this is greater than 0. Right, so if this is greater than 0, then we know it's this case, and that's, good. We can also document the optimal x2 for this. So p comma m here. And this, let me there. Right, and then we can put in the other conditions, right? So this will be 0, and this will be m over p2. And here it'll be m over p1 and 0 here. And we can add these other conditions as well, right? So these will actually, cover everything. So, we'd need to do if m over p2 minus p1 over p2 v prime inverse p1 over p2 less than or equal to 0. And this thing here. And then we're going to also have the same kind of conditions here, right? So if the same condition above for this one, and we also have this condition hold. So I'm just going to move it from here. Right, so there we go. So that's the other condition for this. So we need to check that condition, you know, in order to make sure it's not satisfied. And technically you might need to check, you know, multiple of these, but they're very likely going to only fall in one case, right? So if you find one solution, that's going to be enough. And I'll make sure that that's the way that happens whenever you're solving one of these problems, right? So we've talked about a lot of v's before, right? So these are things like x minus c squared, you know, square root of x1. You know, you could do log of x1. There's a bunch of things, right? E to the x1. You just need these things to really be increasing in order for it to be, you know, make sense. And you can add stuff into all of these as well in order to start thinking about other things. But great. Yeah, so those are some good practice problems that you might want to try. Going forward, so essentially we need to check these three cases. That's what we did on the previous slide. So there's case 1, case 2, and case 3. Recall that one of these cases is ruled out when this is the marginal utility of good 1 goes to infinity. And the case that is ruled out by this is that this one. So this rules out case 2. Right, so that can simplify some problems. And finally, remember, if you're trying to write a general solution of this, there's going to be several cases that you'll need to write out. Well, great. That wraps up the quasi-linear utility discussion. So we discussed how to solve this utility maximization problem with quasi-linear utility functions for a general V, right? And then you can go through and try specific Vs on your own time to get some practice, and there will be one in the quiz. So thanks for listening, and I will see you again soon. Bye.